Okay, thank you very much for coming.
Oh, thank you very much for having me here. And okay, so I will talk about the more minimal problems in the age of machine learning. It's a little bit selling title. There will be lots of minimal problems and little machine learning, but there will be some machine learning. And this work actually started I was visiting Brown University like 3 years ago for something what they called algebraic geometry semester at Brown. And there I met people from community of applied algebraic geometry, and maybe not only applied, but I naturally find most inspiring working with applied people like Tim Duff and Ricardo Fabre is my computer vision person, Kathleen Kohn and Anton Lakin. Peter Huby was my student, master student, who did the paper which got the prize actually at last CVPR. So what's going on here? So I will talk about basically material which is covered by 4 recent papers. The first paper was ICCD 2019, and this is a paper which somehow classifies certain so-called minimal problems. I will explain what minimal problems are and explain what it means. The second paper was a follow-up, actually, which studied broader class of problems, which is much more complicated, much more mathematics, therefore much less visible. but in fact, it's much broader. And then the third paper will be about our first attempt to make methods for solving algebraic equation, which is based on numerical homotopy continuation to be like a practical. And the last paper is making them even more practical and using some machine learning to overcome some problems which are there inherently. So all what we do is somehow related to 3D reconstruction. So this is actually quite old pipeline which we have developed like maybe 15 years ago. So these images are still here. And with some of the students which I mentioned here, with some Slovak students who actually started after that a company which is called Capturing Reality. This is the result from their work. This Capturing Reality company is producing basically photogrammetric softwares. It's a very successful, high quality results. Basic technology was developed in 2 PhD theses of those students in our case, but then of course they made it professional and implemented it in very efficiently. So this is it. Recently, this company was acquired by Epic Games, so it is now basically in US hands, doing games, I guess. Of course, other applications are like autonomous driving. So we have some projects related to this. And another thing is movie industry. So we had a collaboration with a French post-production company, Image, which is part of Technicolor. And they actually integrated some of the student software, which is kind of related to capturing reality of those students, into an open source pipeline, which is called Alice Vision. It has structure for motion part, it has multi-view stereo part. It's completely open source. It's developed, it's maintained and developed by this French company, Image. And they use it to do movie tricks, right? So just combine 3D with virtual things and make tricks. Now, what we are after here is 3D reconstruction. So this picture shows like a cartoon where these are reconstructed 3D points, and these wedges are cameras which fly around, which show the positions of the cameras where the cameras were when photographing the scene. And what I will talk about here today will be all about something which we call calibrated perspective camera.
You need all those cameras to avoid the occlusion.
Yes, of course, there's lots of occlusion happening. So each camera sees something. What we need to see points by more than one camera, like at least 2, 3, 4. In practice, these systems, they usually work like with 10 plus cameras at a time, not with all of them. There are maybe thousands of cameras involved. Of course, this is the output of that 15 years old kind of implementation, which we had. Currently, Capturing Reality can work with thousands of images in tens of minutes. So they really can work with lots of images. And of course, we all know it, like Google Maps and everything. This is basically the same technology, which is built on the same thing. So there is something which is interesting here, why we do talk about calibrated, uncalibrated. In vision, historically, people spent lots of effort and they're lots of interested in uncalibrated setup, which has some interesting theoretical maybe angle. But in practice, actually, calibrated setup is more practical, it's more constrained, things are better conditioned and less free, so to speak. And also for research, these problems are somewhat more difficult, and so we can do a little bit nicer math around them. So people like to, you know, balancing between generality and specialty and to finding something where you can do something interesting. So this is why we work on it. Okay, now this is kind of a general photogrammetric pipeline as we know it these days. So at the beginning, we have multiple images, then we do some, these days, machine learned, in old times, shift-based feature extraction, and based on some similarity distance in a feature space, we do tentative matches. And then comes the key part, which we are interested in here. This is filtering those matches using some geometry of the cameras, which means they are trying to fit the geometry of the cameras in such a way that it is supported by a large number of those matches. And by this, we recognize which matches are correct and which are not correct. Now, this is done currently. The paradigm is to use some small number of data points to fit the camera models and then to evaluate the support from other points. Of course, many of these guys are incorrect, so not all of them will be supporting even the good model, but the assumption, inherent assumption is that the largest consistent set is correct. So if the largest consistent set is supports the correct relative pose of the cameras for a camera model, then we can recover basically good models, even if they are like large, is a large contamination by mismatches. So this is it. So, and now what I will talk about is basically computing these camera models from those small number of data. So this is a problem, computational problem, is a mathematical algebraic geometric computational problem, which leads to solving systems of polynomial equations. And this is what we will be doing. Minimal problems, right? We call them minimal. It's a historical name, of course. One could find another name, and historical name comes from the fact that we use exactly as many data points needed to fix the model and to fix it up to a finite number of possible solutions. So the simplest thing might be a line, right? So I have 2 points, and 2 points in general position give me one line, single line. I obtain parameters of that line, A, B, C in this particular case, as by solving 2 linear polynomial equations in this case. Of course, up to scale, so there are infinitely many such triplets, but they all represent the same line. So this is a minimal problem, right? I have exactly the number of data to fix a finite number, in this particular case, just single one model. What are not minimal problems is like a single point, right? There's infinitely many lines going single point, or there are too many points, so that in general position, there is no line going through them. So this is like 2 cases, right? So the minimal things are just exactly balanced to have this finite number of solutions. And of course, this was a trivial example, but now an example which we know from computer vision and which is famous in some sense and appears in many of those 3D reconstruction pipelines is this problem that we have 2 cameras and 2 cameras see 5 points in space. And if these 2 cameras perfectly see 5 points in space, then we can compute a finite number of possible model of cameras which can explain those 5 points. Now depends how we formulate the problem. So most people are familiar with computation of this via essential matrix, which is sort of 10 solutions. Here I put number 20 solutions, and there is yet another possible, which is 40. So there are like 3 numbers which make sense, 10, 20, and 40, and they differ based on what is computed. So if you are computing essential matrix, we have 10 essential matrices, which then can be decomposed into 20 rotations and translations up to scale in projective sense, or to 40 R's and T's if we consider also plus minus T. So these are different possibilities. And in this paper, and this will we somehow stick with this one, which is 20. There is some deeper thing about
Tomas, which 20? The mirror ambiguity or the scale?
This includes the twisted pair ambiguity, but not like plus minus T. Okay. Yeah, because we consider this T to be a projective entity in this particular case, so plus minus doesn't matter. But of course, you could say 40, you could say 20, you could say 10. And actually 40 and 20 is a little bit more a view, and this is a point of view how you look at it. But difference between 20 and 10 is much deeper. It's about a possibility to decompose a polynomial system into some sequence of simpler polynomial system, which is something that we also try to understand with other students, but it's too complicated at the moment to talk about it. Okay, so in minimal problem, the definition is a 3D reconstruction problem which has a finite number, non-zero finite number of solutions. And there's another important point, and this is that it works for generic means random, means with random noise data. So like if we sometimes these problems are over constrained in a sense that there are some relations on what I have to have in images in order to have a solution. And this is what we do not want in this case. So this is another important thing which makes it much simpler. This genericity regarding solving polynomial equations is actually a very important concept. And we rely on it in many places of these things, because the genericity somehow says that things can go wrong only on very small subsets of data, on something which is like curves or surfaces. So if parameters lie on some surfaces, things go wrong, but everywhere else they are okay. So from the measure point, from the volume kind of perspective, these bad places are just zero measure-like places, so we don't care about them. Okay. Now, the question which we had at the beginning was like a research question. What are these minimal problems? Right? Many people have, there are thousands of minimal problems actually already described in vision. And we thought, well, what about looking at some conditions under which we could characterize some of these problems? And our conditions are that cameras are calibrated and we see points and lines in space, and those points and lines may be incident somehow. Now, the question is, how many cameras can see how many points and how many lines, all these combinations, such that we would have a minimal problem. That means a finite number of solutions to those equations. And this is, of course, very complicated. So we need to have some additional assumptions to be able to handle it. And we took an assumption first on the first paper, which is something we call complete multi-view visibility. This means I have a structure in 3D, and everything what is in 3D projects to all images. So nothing is occluded, nothing is misdetected, everything is everywhere. And I also use information in my equations from all these observations. And under this condition, we actually, for calibrated cameras, were able to show that there exist exactly 30 minimal problems for that situation. So which is like very small number, and in some sense very surprising. And it's a little bit imprecise because in fact, if I have two views, I can always add whatever lines in those two views, because that line will intersect, those two planes will intersect in a line in space, and I will get kind of another problem. I can get arbitrary number of lines.
Say 30 minimal problems, that means 30 solutions.
30 different configurations of points, lines, and cameras.
Okay.
I will show the table of those 30. But I first wanted to say here something that there are actually, for two views, there are like classes. Some of these examples have infinitely many cases because you can add more and more and more and more lines. These lines don't bring any constraints on the cameras, they just bring another line in space. But if we look at this, if we consider this a class, then there are only 30 such classes. So here it's kind of a benign thing, nothing interesting. But if you start looking at situations where some points may be missing in images, which will come later, then this becomes much bigger issue. So this is why I mentioned it.
You don't include the unknown focal length.
No, we know the focal. Yes, sure. Of course, this game can be played for millions of variations of the model. Yeah. Okay, so that's one thing. I will show the examples. And the second thing, we compute the number of solutions. For each of those 30 problems, we compute how many solutions there are. And the number of solutions kind of reflects the complexity of the problem. Because if you have something which is 100 solutions, then you have to solve a problem which is something like 100 times 100 eigenvalue problem. Right? So there's a matrix 100 by 100. So the bigger the matrix, more difficult it is. Now I will show kind of a panel of things which consist of such pictograms. So always look at how many views are involved. Then there is a configuration. In this particular case, this is those 5 points in space, nothing else, just 5 points, no line in there. And then there is how many solutions there are. And this is the result. So these are 30 cases which we discovered. So you see that interestingly, nothing is happening for more than 6 cameras. Why? Because as you add more views, you add more and more measurements. At some point, you have too many measurements, and generically, there is no model fitting those randomized measurements. So this stops at 6. It starts, of course, at 2, and then goes up. You see that the numbers of solutions are, very different. There are some guys which are really bad. These are absolutely impractical, right? This is something which doesn't make much sense. I will explain how we counted these solutions. This is an interesting thing on its own. And some of these things are known, right? For instance, this guy, 5-point problem, this was the familiar guy we talked about before. Another very, very familiar one is just calibrated homography, actually. It has 5 points, but this 5th point actually is on the intersection of 2 lines through 4 points. So basically 4 points is all you need. So this will be calibrated homography. Then there are some other cases which people described before. Joe Kirill, which we also collaborated with in his thesis, which was on trifocal variety, he had these 2 problems. And then if you look at these numbers, some of them are reasonably small, practical, some of them are very big, not practical. So this is interesting. But now,
just to what I remember for 3 points, at which point then go down to 3 points only or 4 points?
Yes, I will talk about it. This will be one. So this is another classical problem, 4 points in 3 views, which is over-constrained as such and must be somewhat relaxed. And because it must be relaxed by not observing something, it's not listed here because it's not full visibility problem. In order to have it minimal, you have to forget about something in one image, and therefore it's not full visibility. And of course, it appears in other tables from the next paper, but in this paper it did not appear because it's not full visibility problem.
I have a question. Is it always possible in all of these cases to just count the number of degrees of freedom?
Yeah, I will come to it. Yeah, it's almost that, but not all of it.
Okay.
Yeah, so how we do it? How we can find these problems? Right? Exactly. There is some counting of degrees of freedom, but this is not all to it. Sometimes there are some like hidden kind of dependencies or something like that. And so for this to have a minimum problem that if you look at these equations, then you can say, well, at a given point, I may look at the Jacobian of that system, and the Jacobian of the system must be full rank. So you can like locally reconstruct. So if I fiddle a little bit in parameter space, I have to be able to reconstruct. So I will show it later. So by counting, we get 39 problems. And by Jacobian text, we reduce it to 30. The counting is it's diaphantic equation solving in some sense, because you count the numbers upstairs and down there. I will show how to do it. So counting, right? So we have cameras, points, lines in space. So each camera is rotation and translation, 3 + 3, it's 6 parameters. And we have to fix coordinate system of the world, which is fixing every first camera, and also the scale of the world, which is 7 parameters. So we multiply number of cameras times 6 minus 7. And then points have 3 degrees of freedom, free line 4, incident line to a point only 2. And the similar thing goes in images, points have 2, free lines 2, and incident lines has 1. And so we have to count these guys, and what's upstairs must be matching what's downstairs, right? So for instance, this is a minimal example, which you know are familiar 5 points in 2 views. So we have 2 cameras times 6 minus 7 plus 3 points, 5 points, 3 times this is 20, right? And then we count in 2D, 2 views, 5 points, 2 coordinates, again 20. So is a candidate. And indeed, if we check it, this is a minimal example. But there are some guys which are not minimal. This is a peculiar guy, kind of hedgehog guy, which has like single point and 8 lines through this. And that guy has a count which is 42 and 42, but actually has infinitely many solutions because the Jacobian is simply not full at the point. So this way we counted and did it. So it's not very complicated. In fact, this is something which one can follow relatively easily. It's like a 1 page of arguments, more or less, in the paper. Nothing super special. Later, when I will show some cases where we forget about some points, it becomes much more complex. Needs really a brain to do it. And we had Katlan on, and she was able to do it. And this diaphantic counting in very complicated setup. So it is okay. So this was about the Jacobian. Basically, again, it just says that if I'm here in space of images and I won't fiddle my measurements, so I want to have locally reconstructible situation upstairs, which means that tangent spaces must have the same dimensions of those things downstairs and upstairs. This is easy to do. to check, because you just fabricate certain case, you take a scene, you project it, you fabricate kind of a simulated case, and you evaluate the Jacobian. And because of this genericity principle, it's enough to evaluate single Jacobian at single point, of course, a regular point. You must pick the regular point, but chance choosing non-regular point is like very small. So in some sense, some people consider this to be a proof, some people don't consider it to be a proof because you still have a chance of hitting something back. But normal engineers, they would just try some points and they see it works and then it's okay.
So some point you make solution.
Yes, you basically what you have here, equations which describe those solutions. Then you find one solution, you may fabricate it, for instance. So you create your cameras, points in space, you project them, you put those parameters into your equations, you compute the Jacobian of those equations, and you check the rank of the Jacobian in one point. That's.
And is this not related to the implicit function?
Yeah, well, the Jacobian thing is related to implicit function theorem, but the fact that the genericity fact is not really perhaps. The point is this, so when things fail, right? When things fail if something is dependent, if something is satisfied. And the something is satisfied in terms of algebraic geometry is always algebraic equations. But some algebraic equations must be satisfied. So if I have a parameter space, I have to satisfy algebraic equation, even a single one, I will get a surface in that space, right? The surface is a measure 0 something. It's just, if you take a random point somewhere, it's not on that surface, then something fails. So we will come maybe to it a little bit later. Okay, so counting the solutions, that's another big business. So this tells you that you have a finite number of solutions, but how many solutions you have, this is tricky. So for that, we do, again, genericity thing. So formulate an example and solve how many solutions that example has. Again, simulate and solve. And again, genericity tells us that for almost all parameters, almost all generic systems have the same number of solutions. Of course, in complex numbers, right? In complex numbers. So this must all be done in complex numbers. In real solutions, this is super complicated. And depending on the parameters, we have different counts of real points at different places of the space. The parameter space is actually split into chambers by something which is called the discriminant of the system, which is basically a big polynomial, super big polynomial, even to evaluate, usually not possible, not definitely for these programs. And that these chambers have like different number of real solutions. And if you go from one chamber to another, you have to pass through doubles for multiplicity solution that the Jacobian rank is deficient, right? As Jacobian rank goes down. So of course we have to, but in complex numbers, the number of solutions is always the same for generic things. So this is why we can do it. So there are two approaches how to do it. One is symbolic numeric approach. That symbolic, which is not numeric at all in some sense. So we fabricate a generic random instance. Then we compute the Gerbner basis. What is a Gerbner basis? If you have a linear system, you do Gaussian elimination, and after Gaussian elimination, you get the Gerbner basis for the linear polynomial system. That means new system, which is somehow simpler. Simpler in sense that you have one equation in one unknown, to another equation in two unknowns, three unknowns, and so on. And you can solve gradually and back substitute and do it. So the same thing can be done for general polynomial systems, just it's more complicated. Algorithm is a generalization of Gaussian elimination, can be done, can be always computed, has a small problem that is exponential in size, it's X-space problem. So for problems which have more than 3 cameras, this is not really doable. So for 3 cameras, this can be done. You compute this Gerbner basis, you solve it, you find how many solutions you have. There is some trick here which I don't want to talk about. Simply you count something and it gives you the number of solutions. But for more than 3 cameras, this doesn't fly. Too complicated. For more than 3 cameras, we use a different technique, which is numerical algebraic geometry technique, which is based on numerical computation. So the symbolic ones actually prove something because you symbolically manipulate equations and you can really count. So this is a provable. These techniques, they are not provable, they are just numerical. Actually, there are provable variations of that, but no one dares to run it because that usually takes forever. So what is happening? So here is the parameter space. This is like coordinates of points in my images, right? This is 5 points in one image, 5 points in the other image, which is 10 plus 10, which is 20 numbers. So down there are 20 numbers. Up here, for everyone, in this particular case, I have 3 solutions. we could think this would be like absolute post problem, right? Absolute post problem, something simple, which is like small number of solutions. So the idea is that I have one problem where I know the solutions. And here I have some other problem where I don't know the solutions. And I will interpolate between these problems in the parameter space and will somehow deform the solutions from the known system to the solutions of the unknown system. This has developed technology. Method is called homotopy continuation. It must be done with care because these red things are exactly where you see there's only like a fatal solution at that point. So there is this exactly this multiplicity solution that the Jacobians become singular, and therefore you cannot track using Jacobians to that point. So that everything fails. But the theory says that there is always a path avoiding these bad things. There is always a path. Of course, another question is how in practice to generate such paths, how to do it efficiently, and so on. For that, there is a technology developed by math people who do this numerical computations. And now, so this is how to solve it. But we don't want to solve actually. I don't want to count how many solutions there are. But a variation of this technique can be used to count as well. The idea here is that I fabricate one point. That means I take my cameras in space. I take points, I project. So I have my camera position. This is the solutions, the camera positions. And here are my images, right? So I know one of them, which I fabricated. I don't know the others. Instead of going from A to B, I will be now rounding around, going from A back to A. And that will create that this solution will travel on this kind of a cartoonish surfaces, and it will actually visit all the solutions upstairs. The fact that it visits all the solutions upstairs is a non-trivial fact, which is coming from like analysis and algebraic geometry, and it's important that you visit all of them. Of course, you have to encircle here somehow nicely those singular points, and you have to go along sufficiently generic passes, so you don't have actually in practice guarantees. But if you circle a lot and you still see the same numbers for a long time, then you can believe that this is a good approximation of the true number.
Does this have a big O complexity on how many times you have to do it or not?
No, don't know, frankly. But I think there are lots of results about this. There are variations of this technology which is like provably correct. So they have kind of like step control and things like that, but I don't know much about this. We don't do it, of course, because it's not really that interesting for us.
But when you speak of things like generic field or generic problems in the other analysis space, are you thinking of specific instances you're constructing, or
yes,
you construct specific
random points? You take a random 5-point problem, right? You would take random 5 points in space. You would take a random 2 cameras, simulate it. You would project it. You would do it in rational numbers, maybe exactly, so that you can really do something. Webner basis technology must be done in exact computation, because if you change one coefficient, suddenly you have no solution, right? If you just round somewhere, it's exactly not really solving, right? This one is not exact. This one is approximate. This is floating point arithmetics. This is just numerical thing. But symbolic methods, they must be exact. So you have to do rational number. You have to compute in integers, right? Because you always include denominators. So everything. But integers are big. These numbers grow. So sooner or later, your coefficients are megabytes. Basically, it's a problem of that approach.
So you said that you take the output of your problem, then you will hit everything. But how do you know? So how do you know which other problem has the same output?
So this
you fabricate the first, and
yeah,
how do you know the
one
other?
point here means the high dimensional point in parameter space. So if I fabricate something, what I do, I just take my 3D points, my cameras, everything. So here are, let's say, positions of the cameras and 3D points. Every point here is like the 3D reconstruction of the scene. And here is the point of images. So if I construct one thing, I create maybe this one, that one, or that one, I don't know which one, but I create one pair of these 2 points, like parameters and the solution. Okay, and then I start going in parameter space randomly, like a random passes. I just have to only come back. And here upstairs, it must go back again somehow. Of course, sometimes if you do a small loop here, it will just do a small loop here and will not come to a different point. But if down here you encircle this these singularities, these bad points, then this must go to a different point. But that, of course, I can't explain. That's like this page is from Hatcher or something like that, right? So it's a fact. It must be taken. And of course, if you are unlucky and you hit that place, then you get here to a point where Jacobian is singular, and because for the tracking we use the Jacobian, I will show later, then this fails, just the thing crashes. But the fact that you visit all of them, it's non-trivial, so you can't explain it. I don't know how to explain it.
So you just check the reprojection error or something as you're traveling on this path.
Yeah, you have to be solving the system, those equations, basically, right? You have to be solving those equations. And I will show it. I will show it in a second. Okay, so this was the first paper. I will talk about this later. Then another paper which came after was said, well, come on, so we have all this complete visibility and so everything is simple. So let's look at case where I can forget something in my images, right? So here I have an example. So I had 4 points in space and line in space. But in the first view, I did not detect the point. And in the last view, I did not detect the line. So now this is much more complicated because you can always add more views and remove something and it will balance and you will have infinitely many problems. So there is no hope to have a finite set anymore. So of course, we started taking some additional assumptions to be able to do something. First of all, we said, well, let's look at 3 views only, right? That's the first interesting example. 2 views, there you can't miss much because then you don't have the reconstruction. You have to see it at least twice. So 3 views is the first non-trivial interesting case. And still it was too complicated. Still it was too complicated. And the complication was coming from the cases where a line would be spanning more than 1 point because it somehow entangles things together. So we could not handle that thing. So we said, well, let's forget about these cases and let's consider the situation where every line must be incident to maximally 1 point or to no point. So you can have a point with many lines, but you cannot have a line with more points, right? Okay, so still there's infinitely many problems, but we kind of split those infinitely many problems into kind of a classes, and each class can be in some kind of reduced to some representative situation and can be classified in that way.
What do you mean infinite? So specific number of views are there?
Yeah, you can add more stuff in the spec in the more points and more lines there in 3D, right? And then you can start removing what you see in those images. So you can always balance this number of observations versus number of parameters, because if you add a point in space, you have to reconstruct that space. That means you add 3 more parameters to compute. And then you project it to 3 views, and you add you add 6 more parameters to observe. But if you forget it from one view, there's only 4, and forget from another, only 2. So you can balance this. Yeah, so there is no, if you observe everything, you have to have everything, and therefore it stops somewhere, because if you have too many observations, they can't be independently chosen to give you 3D stuff up there, because there is some kind of balance. But in this case, no, there is no hope to have a finite number.
To be useful at all, any entity has to be visible in at least 2 views.
Yes, sure. And there's always this problem with adding some lines which actually bring no constraints on the cameras and so on, and this makes this problem much more complex. It's complicated. Paper is there, it's readable, but it's super complicated. But still, we got something. 74,575 different classes. Of course, computed by computer. And we counted solutions of some of them, but of course not for all of them. Some of them may have too many things. So we look at those problems which are less than 300 solutions, and these are some cases. So we have always like how many solutions there is, and how many problems have that number of solutions, right? So some of them are good, like 160 is still not too terrible. This is still practical. This is still computable, and there are quite a lot of those guys. And there are also some guys which have no incidences, which are like no points are on lines, just everything is kind of free. Some of them are familiar, like this one, for instance. You see 3 views, those two views are actually 5 points in two views, and the third one has just 3 points. So these are absolute post problems. So the combination of one relative 5-point problem with one absolute 3-post problem, and all other variations. And we can look at the numbers here. Again, these numbers can be, some other people, if I formulated it a little bit differently, could get a little bit different numbers. Some of the problems could be reduced potentially to some sub-problems and make it simpler. And we don't know the full understanding of this reducibility. We know for complete visibility which problems can be reduced and which can't be reduced, because this is controlled by something which is called Galois group of the system. And the Galois group is basically, as you saw, these solutions traveling upstairs. So each round downstairs create one permutation of solutions, and these permutations form a subgroup of the symmetric group. And that subgroup is called monodromy group. It's basically the Galois group. And the structure of that group reveals whether the problem can be decomposed or can't be decomposed. So this can be computed. We can do it. For the complete visibility problem, we have done it. We know that almost nothing can be reduced, but something can. Okay, so these are some problems which are interesting. Okay, so this was classification work. Now, of course, it's nice to, we have many problems to classify. The questions can be really solved, right? That's a problem. So we look at some point with this multi-author paper, which had people from the algebraic community and from vision community, basically people working together at ICEM in 2018. And then they got together some examples, and we look at two problems. Those are from that 30 problem list, and the one is like 3 points in space plus 2 lines, so 2 points, and another one is just 3 points and a line in space. And the first guy has 312 solutions, and the other guy has 216 solutions, and this is the area code of Chicago, this is the area code of Cleveland, and we have now this 272 problem, which is the 4 points in 3 views, which is 272. What's the code of 272? This is not far from it, Scranton. So we have a Scranton problem again. This is 272. So it's a little bit of fun, right? So, anyway, we did it by solving homotopy continuation. We tried to, and this was really like an implementation paper. So we took the homotopy continuation technology, which is in various mathematical packages, and optimized and engineering and so on, and got it to solve such a problem in half a second. Frankly, half a second is useless, right? It's not interesting because you have to solve the thing thousands times per image. So this is not useful actually, but previously these methods could do it in like tenths of seconds or minutes or something like that. So we just wanted to push it down and see how fast. And we see the problem is that you have to track 312 solutions. That's the problem. And actually are interested only in one at the end. And this is what we will address after. So these are these two problems. And let me just say something about homotopy continuation. What is it? So I have my system, which is called G. This is a parameter space T, some parameter which is affinely combining known equation with an unknown equation. So this equation, I know the solutions. Maybe this is, I know I have 4 solutions, right, of my system. So how to create a polynomial where I know the solutions, that's 4 solutions. I take the 4th root of unity. I know very well what are the solutions of x to 4 minus 1, perfectly, 4 points on the unit circle in the complex plane. So I know them. I don't have to compute them. I can synthesize them. And then I have this system, and so this is my G, and f is a generic polynomial of degree 4, right? And I just tell you this is a parameter t. This is a real parameter going from 0 to 1. And this gamma is some kind of thing which makes sure that this thing is traveling in the complex plane, not in the real plane. The problem is that if you were in the real numbers, you would inevitably hit a point where there is Jacobian is not full rank, and the thing would fail. So to avoid it, so you just need to put there this gamma. But if you started actually with a square root 4 roots of unity, this would not be so big problem because, yeah. Anyway, but that's something. Now, what to do, how to track the solution, right? So what you do basically, this is like the path, this is parameter downstairs, and it will be one of those solutions. So basically, as you change the parameter, the solutions go blah, blah, blah. What you do, you numerically predict tangent line, and then you get all that solution. Suddenly, equation is not satisfied. So you take Newton method and you do 3 steps, 5 steps, 10 steps, and you correct it. So you basically iterate this predictor corrector thing. You can consider it's Newton plus method, local method, which checks it. And this way you can get from a system, from a known solution to a unknown solution. This is done independently for each solution. So you can parallelize it actually, and can be done independently, and can be modified in many different ways. You have to avoid singularities, and if you avoid them, then you can prove that this works. Again, this was just counting thing. I think I talked about it already. Okay, so we did that. So from the speed point of view, this was not a really big breakthrough, but what was interesting that these programs were actually quite well behaved. So this the numerical quality of the result was good. Cameras are actually well estimated. So it was like a hint, yes, 3 views are actually interesting, even numerically, practically, this gives something.
What do you mean numerical? This is after average, after the squares or not?
No, this is a minimal problem. This is just from the minimal number of points, which means exactly three points and 1 line in 3 views, or 3 points with 2 lines, so 2 points in 3 views. Only from this minimum data. Some of these problems are difficult to solve because numerically you solve a complicated system of polynomial equations, and you have to do it numerically at the end somehow. There must be some kind of eigenvalue computation problem at the end, or something like that, or this homotopy continuation problem. So it's a numeric, so you round, you may fail, you may lose the pass and everything. So you a priori don't know if the problem will be useful or not useful, if your formulation will give you stable algorithm or not. This is an open question and must be really studied per problem and understood what's going on per problem. And so this was this was like, encouraging in the sense that we say, well, 3-view problems are actually interesting because frankly, no one is using 3-view problems these days because people didn't know how to solve them practically. So they did not put them into the solver. So everything is 2 views based until now. Okay, so this is it. Now,
when you say solving, you mean all the solutions, or just taking one solution?
Yes. Very good point, and we come to it. I just show something here. Exactly, all the solutions. Where are these solutions coming from, right? You at the beginning you have some geometrical problem. Then you formulate it in equations. And because you solve equations, you can use only equations. So for instance, you can't use inequalities in this particular case. You cannot say all points should be in front of cameras. And because in that case, you may get solutions where some points are behind cameras, some points are in front of cameras. So all these 312 solutions for Chicago, which you have, are basically 311 are spurious things which are due to some relaxation of your formulation or algebraic formulation of the problem. So in fact, you don't want to solve these guys. You want to know which one is that one which goes to which is the one which you want to use at the end, which really corresponds to all other constraints which you could not use in the computation task. Of course, this seems to be like a nonsense to know it beforehand, because how can you know which solution here should end up which solutions there? There is no general theory for it. Anything can happen in general. Still, it turns out that it is somehow possible to train an oracle or to construct an oracle which is not completely stupid and which with relatively high probability hits the right starting point. That's something which no one would expect, perhaps, but it works. It's interesting. It doesn't work always, so it's not 100%. It's actually that example which I will show is actually like 25% successful, but it's enough to make it actually useful and working. So this is what we want. So we thought, well, let's not solve all 312 or 272 or whatever number. Then look at what we get and throw away everything, which is except for one, which we like. Let's try to somehow, based on measured data, predict from which guy to start and only track one path. So make it 300 times faster. And not only that, but in principle, this allows you to actually work even with problems which have infinitely many solutions next to those finite number of solutions which are interesting. So it allows you to even more relax your equations and make them even simpler in some sense, because you don't have to care about some spurious non-zero dimensional components. So this is something which is also important. So in some sense, it allows it frees you from this curse of multiplicity solutions. So it doesn't matter if the problem has 100,000 solutions, if you always can hit some small subset which is interesting. Well, of course.
Without the model, these are random instantiations from 312, right, which go to the real problems, correct?
Yes, I will show it. So the one question is how to choose these original guys.
Yeah.
Another is how to pick the one to start from for a given particular problem. So and we did it in these two pieces, and I will show. Right. So here you could say, I mean, and there's another thing. If this was done in complex numbers, I could actually start with a single case, single complex case, and always homotopy from it. And then I would, but of course, the problem is that then I would have to do everything complex numbers, which is one it's like more computation. That's one thing. And another thing, it doesn't really capture this locality of the problem as we found. So we did it in real numbers only. I will show it. Okay, so what we in general theory says, if you want to have this successful, you have to do in complex numbers. There's this gamma thing, the gamma number. But we said, no, forget it. We will not do it in that because we will fail anyway. So we don't care if we fail sometimes on the boundary of those cells. Maybe we need to get a single point inside of each cell so we can start in each cell from that point. Of course, this is unfounded kind of idea, which may be completely wrong. So nothing justifies it, only that it works at the end. So but we did it. So, and it works. Okay, and then, which problems to look at? We could look at Chicago and Cleveland, but no, we did not look at that guy. We look at this guy because we like this guy. This is this 4 points in 3 views, which is a notorious problem which has been studied for a long time. People tried to develop simple solvers. They failed. The only solver which is fast is from Shafalitsky and Istad from 2004. And it's complicated approach. It's not a minimal problem. It's kind of optimization problem because the problem is over-constrained in its original form. So if you take 4 points in 3 views, this is over-constrained. And for a data with noise has no solution. So it must be relaxed for this to become minimal. And relaxation may be, for instance, thinking about that you actually don't observe a point, but you observe a line there.
Or one coordinate.
Or remove one coordinate, or add another variable which corrects one coordinate, which is actually what we do. And that minimal problem gives you 272 solutions, which is too many to get practical solver. And we worked on that for years, and no one could get a solver. No one got a solver. Mr. Shafalitsky had their solver, which I did not know any implementation of that until recently. When we had this paper, then another my co-author actually said, yeah, come on, I have implementation on Mr. Shafalitsky somewhere, which runs like 100 microseconds, so which is actually quite fast, but still. Okay, so what we did, on input, you have 3 images and 4 points in them, but 1 point is somehow relaxed. So we like correct this new unknown 1 coordinate. So to make it, so we have actually more parameters, not only camera poses, but also 1 coordinate of 1 point, which is corrected. Then you take this roughly 20 dimensional space. There is some normalization, some kind of invariantization of these things by rotating the camera such that the centroid of these points is in the origin and so on, which removes lots of variation and which makes the learning much easier. And also reduces the dimension of the problem to 14 or something like that, to 16. And then we enter this roughly 20 dimensional vector to a multi-layer perceptron with 7 layers, very simple thing. So machine learning 101. Our biggest expert on machine learning was Peter Hilby, who was a master student after his machine learning 101. So they told him to use multi-layer perceptron. So he used multi-layer perceptron. And of course, also he has to use something very simple because he must be fast. He must be fast. If we are not fast, this is completely useless. So we must be fast. So we want to be something in terms of tens of microseconds. So this model has to be evaluated in 10 microseconds or 5 microseconds. And then we need to do some homotopy continuation, which also has to be fast. So again, implement it in some optimal way in using some particular formulation of the problem, which gives very low degree polynomial equations. So Jacobian is very simple, sparse. So this all can be done, and altogether it's like 16, 17 microseconds, this process. So this,
It's yeah, puzzle. What's your actual, when you train, what's the criteria?
I will show. I will show. I will show.
Is it optimize or optimizing the time or the quality?
I'm optimizing this model. I will show that. I will show it. That's a good question. I have to show it.
Good, because I
Okay.
didn't want to ask because I thought maybe that's a stupid.
No, not at all, not at all. So what we do, what we train, we want to train a model which we take some pre-selected number of starting points, which we call anchors. We select them, I explain how. And then this model just classifies sort of based on the input data, picks the model to a point from to start from.
So you know what you expect and you classify the model that gets you
To the target. So, and then my criterion will be to tune parameters of the model such that it will select the starting point from which I get to the target.
Okay, good.
Yeah, and I will explain.
Just
So-
to make sure, this is during usual inference, it's just one pass, you don't optimize.
Just one pass.
Yeah.
But of course, by optimizing, I mean the training, right? Training is the optimization task. So
Yeah, but that you run it on many instances.
yes, that I run many instances. So I take the data set, like 3D data set from ETH, which is like experimental data, reconstructed by Colmap, by structure from motion pipelines, so there are real points, real cameras.
For many RFTs, not just one.
Tens of thousands, 10 million of programs. Each program is like particularly 3 cameras and 4 points, right? This is each, that's the instance. You sample it from the reconstructions. There are thousands of cameras and millions of points, so you can take some samples from that. Then, so each point here I make a graph, and each vertex is exactly this configuration: 3 cameras and 4 points. And I do homotopy continuation between one problem and another problem. Run the homotopy.
So just, couldn't this also be done completely in simulation? Is there a release?
Yes, could be. Yeah, absolutely. But, you know, we believe that it could be done, absolutely. But, you know, we want to publish it. So
The training data,
you want to publish it, right?
the training data is all I'm saying.
Training data is, can be, of course, simulated. I believe this will work the same way, but you want to publish it, so you have to reveal it. Come on.
Can I ask a question? So your model, you wanted to pick just the one starting point?
Yeah.
Could you also maybe take just a few candidate
Yes,
points?
we did that. We did many kind of variations, which we learned to call ablation studies, and and that helped the paper actually get so regularly. So we tried this, you know, like starting with 1, with 2, with many doing a real homotopy, complex homotopy, you know, all these kind of variations, various variations of normalization and all that, because, you know, people, of course, obviously say, come on, why don't you do it this way? Why do you do it this way? Why don't you do it that way? So you have to do some cases and choose the one which works best. So we did lots of variations, which are described in the supplementary of the paper. So not of course everything, just something which will seem to be meaningful at that point. Anyway, so I take these problems and I try to homotopy from one to another, right? To make a complete graph, but of course, some guys cannot be turned into the other by my homotopy implementation, because I do a real homotopy, so I can never go through the barrier of multiplicity solutions. I am sloppy. I want to be fast, so I don't control the step size in the right way. Just, you know, something brutal. But anyway, I have something which gets somewhere sometimes and sometimes doesn't. But I can measure, I can construct that graph, and then I can select a subset of vertices such that I can get to everyone from one of the vertices, which is something which at least vertex cover of the graph. Again, people say, oh, come on, this is can't be done. This is NP complete, of course. Now, who cares that it's vertex cover? We just do something greedy, which approximates the vertex cover. Again, it's important to call it vertex cover because you want to get it published. But you get something, right? You first select this set of starting points from which you can get everything. And of course, you don't have to get everywhere. You can say, well, I want to have 100 starting points. How far can I get? 60%. if I another 175% cases, and then you balance just how much work you want to do and how often you want to fail. Okay, so basically, this training data was somehow constructed. Maybe this slide is too dense to go through it. So again, construction, and then what we really do is that we know that we know from which one we get where, and so we want the model to predict the one which can get us to the goal. And if it gets us to the goal, then we say yes, good, and we don't add anything to the loss. If it doesn't get there, we just add something to the loss, and then we train the model. Now, altogether, this guy actually is not that great because it succeeds only in like 25% or whatever cases, 26.3 here. So 3 times out of 4 it fails. Okay, so it seems to be useless actually. But fortunately, because we use it in a Randstad scheme, so we can provide more data for a given configuration of images. Interestingly, these additional samples can sort of remedy this problem. So interestingly, it's not the case that we would have some camera configurations that everything will be failing. No, it's somehow related to the 3D points rather than to the camera configurations. And so if you sample 4 times more points, you actually get it reasonably good. And if you count 4 times more points, then at the end, your effective solving time will be 65 microseconds. And 65 microseconds is efficiently very useful. This is good, right?
Does the homotopy continuation computation have any kind of hyperparameters that need to be fixed that you're training on?
Sure, it has. It has.
It
It has the step sizes, the method of predictor, the method of corrector, which is Newton method. So, but you know, Newton method, we do 3 steps. If it doesn't converge in 3 steps, it doesn't converge ever. No, just predictor, we do something, right? Just we did various experiments like without predictor, just do Newton guy, more steps of Newton guy, which is much faster. On the other hand, it's much less predictable because then if you do complex number, then basically this gives a fractalish kind of behavior if you are not converging. So it's jumping around, which also may be good because sometimes jumps somewhere where it converges then. But you know, it did not. When we used that one, it did not train so well. We could not train it that well. Still, we were only twice slower than this one. Yeah? So there's lots of engineering behind this. And interesting is, I believe, is that we can balance this kind of and you know how much you succeed depends on what you use. So if you use complex homotopy and you spend much more time in that, of course, this number will not be 25%, it'll be 75%. So is this all about, should I be weaker in this part of the algorithm and compensate by something else, or should I be, you know, it's a multi-dimensional optimization problem, very complicated, but still we could, you know, squeeze something interesting out of it. So that was it. Okay, and people like that because it's machine learning. Okay, and that's basically what I wanted to say. We try to apply it to other problems now, and it seems to be working somewhat. We will see. Not everything has been tested for the new problem we are solving, but it seems to be a reasonable approach, which in some sense can be generalized. Of course, you have to train for every new problem. You have to train for every new problem, but you don't have to have a Shafalitsky's brain in order to crack some equations which no one else can crack, right? So in principle, anyone can train. Yeah. Okay, thank you.
Great, Thomas, questions? I can start with a question on when you start for the ones start from the left. For those, you still have to compute the Grebner basis and compute one set of solutions.
No. Again, this here. I want to say this. Okay, maybe this picture. So here is the set of parameters, right? So I have my 3D data, which I reconstructed with Coleman, with some other method.
Yeah.
And that gives me points in images, of course, which I measure in images. Gives me also points and cameras in 3D space. So I have one point
You
here
have the parameter.
Yeah, I have the
point in
parameter.
the parameter space
Yes.
because you constructed.
because I constructed.
Yeah, yeah.
So I can do one case here. I don't know others. Actually, but the one which I want, I get.
Yeah, I get. Yeah.
Also, I don't care about others actually, for training. I just have only that case which I want to have.
What do you think about predicting the inliers? So everything is about inliers here. What do you think about predicting the inliers with
Predicting what?
the inliers?
Yes,
Because
yes,
this is
yes.
just for the inliers, right?
People do it.
Predicting inliers 1 or 0 or some soft.
There is
specific-
that.
specification.
Yes, understand. No, so there is this Ranftels paper called Ranftel and Coltoon ECCV 2018. No, maybe yes, the one in Munich. There was a paper they trained something to exactly for inliers and two-view matching. There's another paper from which is DSAC paper, which is like a differentiable Ransack kind of thing. What was it? I forgot. And they both actually, it turns out, are related least squares at the end. So they are like train something which is then doing a related least squares in a way. And I don't know, no one uses that. Frankly, I don't think it's competitive to Ransack at the moment. It's a very interesting thing. We thought about what to do with this, whether I try to, and I have a student and she's looking a little bit into these things, but yeah, but it seems to be something very hard, and no one really has anything which would, I believe, compare to Ransack in the quality. And also the problem is that there's this kind of this connection between structure for motion community, all the people who did these things, and new machine learning community. So if you look at those papers, or like Noah's, that's Snail's paper, right, which is on this again, learning relative camera poles from images. Noah, who was the one who built the first bundler system, right? He knows everything about that, but his experiments are, of course, contrived experiments. They don't really compare it to a state-of-the-art thing. They compare it to something OpenCV Ransack, vanilla Ransack. And so why? No, because no one expects us to do it, right, these days anymore. So just compare it to other machine learning papers. So I think this is disconnecting somehow. New results are coming, but I'm not, it's so much work to make it comparable. It's so much work that no one does it.
Oh, okay.
So I'm just curious what you think the learning system is ultimately picking up on. Because basically what you're pointing to is that these are not effectively.
No, I don't think so. I think, no, I'm not saying that. I think it's very interesting, and these learning things are very effective sometimes. And the optimization in other communities like the computational chemistry and that things, people train optimizers. So instead of designing by Newton's step control, I will train thing on the data to do that fit to my data. So this is what people do. I'm really complaining that we don't do it in structure for motion. That's.
I guess my question is this: part of what you're pointing to here is that the class of polynomial systems that we're faced with in these kinds of problems are not random. They're not actually.
No, they are not random. Yes,
There's deep
exactly.
structure in here.
Yes.
Derived from the fact that we have underlying
Absolutely, yeah.
geometry that this is somehow able to key in on.
Yes, yes.
Wondering if you have any thoughts about.
Yeah, frankly, we don't understand it. I mean, this started with the fact that Anton Lekin, he took some homotopy continuation and then randomly generated something. And suddenly we saw, come on, I have starting 7, 10, 6 starting points, and I can get to 60% of cases, which is something not expected. This is something which should not be, in some sense, right? Like one starting point in a real homotopy covers like 25% of cases, which is strange, but it is like it. And it's a little strange that we did not want to do the training at the beginning. I thought, well, we will, I have my starting points. These are points in the parameter space. So I take new parameter points. So where to start? No, start in the one which is closest, right? That's the most obvious, but that did not work actually. That Euclidean distance assignment, that retrieval kind of assignment did not really work. So, and there had to be something more trained to work better. So there is some kind of structure, which of course we don't understand. And yeah.
Nice job.
There's no one first. Yeah.
Well, I don't want to privately on that, but here is a question. On one hand, you have shown mathematically to prove certain steps in your reconstruction that they are under those circumstances or other conditions that you have derived those theoretical results. That's wonderful, and that's what we have to do in the end. So the question here is, since you have this theory, can this theory, what are the limitations of your theory? Namely, I can imagine there are different domains, the urban domain versus the medical domain where you have one curvature and so forth. How transfer is your theoretical results from one domain to another domain?
So,
Because,
yeah.
I used to be at Berkeley, and there was this woman who claimed that, which I objected heavily, and I didn't make friends with that, but she claimed that she has a system that is transferable to anything and everything. And of course, I don't believe that. She's at Stanford currently.
Yes, yes.
She's making the same claims.
Okay, so this, of course, the theory is an algebraic geometry, so it describes everything related to polynomials. Polynomials. Then, if you can go beyond that, you can polynomial equations. Polynomial equations.
How high in polynomial can we go?
Theoretically, however you want. Practically, of course, computational resources are limited, but theoretically you can go this polynomial equations and non-equations. And something is not zero is also describable. But what is not describable in this way, any number of variables and any kind of polynomials. So the general theory is that every polynomial system in any number of unknowns and any degrees is decidable in a sense that you can say, does it have a solution or not? And if it has, then you can find the solutions. And the algorithm is this Grabner basis computation, which is a generalized Gaussian elimination in some sense, which is theoretically solvable with only small problem that is X space problem. So it's double exponential in the input in space. So it's not difficult to write down equations which you can never be able to compute because they need space bigger than there is atom in the universe. No problem. So, but of course, there's a lots of structure. So there's a lots of game can be played. Then another step are inequalities. If you put inequalities, you go to much more difficult space because you have to have ordering. You have to say something is bigger than something. This cannot be meaningfully done in complex numbers because complex numbers, if you multiply, they just go around. So you cannot make ordering and multiplication in complex numbers compatible. Therefore, you cannot make it ordered field or ordered something. And then this doesn't work. You have to go to real numbers or something which is ordered. And that makes everything much more complicated. So algorithms which we also use, which can deal with these are optimization algorithms, which can kind of do some kind of optimization thing. And these are much more complicated things, but can be handled. And then there is another thing which we look at now, which is called tame geometry, and which somehow generalizes that. Tame, T-A-M-E, T-A-M-E, right? It's like nice, well behaved, not wild. And this is something which comes also from algebraic geometry, from Grothendieck, and it's new, relatively new thing, and it goes beyond polynomials. And larger language of functions. So nice functions can be there, but not all functions, like sine, periodic functions can't be there, for instance, but exponential something. But, I mean, these are theories, and the problem is that theory for computation, the price for proving it or being sure that it works for all cases is sometimes unbearable. This is too big, practically. So I cannot, we can, of course, everything that was here, these numbers, it can be computed. If you had enough time and space, you can exactly compute it. This algorithm is simple. It's just, it's Gaussian elimination plus, nothing more.
Have you trained this model that will help you pick the starting points for the numerical method? Are we able to look at its outputs and interpret that it's able to classify some kinds of problems, treat it as a classifier for like?
Yeah, it is a classifier. I don't know. We were trying to get something out of it to make it working, and we did not philosophize much about like what it means. It, in a sense, you fit a function, right? So it's a function fitting, all this training and learning. So what else? So I have a function which is sufficiently complicated, and I just approximate what there is, and I fit it somehow. And we did not. And there are many other possible ways, perhaps, how to formulate it. This idea is making it like a classification problem or a retrieval kind of problem, right? Prepare starting points and pick the one which leads where you want to get. It was just happening somehow that we wanted to, to get something done. And other approaches are definitely possible, like kind of a metric learning thing or whatever. Why not, right? Our metric non-learning, that means just finding the closest point in the Euclidean distance in the parameter space, did not work. But maybe if you train a metric, if you train an embedding, which would give you a different space that might work perfectly fine.
So in primarily testing heuristic methods are very effective. So do you have perhaps, I don't know how you could prove that, but have some guarantee that if this and this and then you can prove with probability?
Yes. This exists indeed, and also actually the computation methodology now for exact methods. This is heavily relying on kind of a genericity and randomization, because if you want to really compute exactly with big coefficients, then this is not efficient, right? You have to basically store strings of numbers. So people normally what they do modular arithmetics. That means you compute modulo a large set of prime numbers, and then you can reconstruct by congruence relations the result. So like the state-of-the-art solver for Gebner basis is doing modular arithmetics. Basically solves everything modulo prime number. Also, what is useful for proofs in some sense, for finding like the number of solutions. I actually don't have to compute exact solutions. I can compute in a prime field. And sufficiently generic prime field is good enough for it. So it works. So it's much, much faster. So for these things, we do it actually in prime fields. So because otherwise it would be maybe not even computable. And of course, we risk that it fails. But if it doesn't fail, it did not fail. You have it. So you have it. So it's proven. But of course, it may fail, and then you don't have it. But normally people try, and there is theory about that. You always have a prime number which works, because in your computation, there is a biggest number somewhere. So if your prime number is bigger than the biggest number which is there, then of course it will work.
Thank you very much, everybody, for coming, and thanks.
Thank you.